In this work, photoparalytic spectroscopy was used for optical absorption coefficient measurements for nanosilica colloidal suspensions at 3 different wavelengths in the near infrared. In the first place, let me give you a brief explanation about this technique. Photoparalytic spectroscopy is based in photothermal phenomena. These are physical phenomena which takes place due to heat generation after absorption of modulated radiation. There are a lot of applications of photothermal techniques. They can be used for thermal and optical characterization, for qualitative and quantitative analysis, and medical applications, among others. The qualitative description of this technique involves a heat diffusion problem across various layers. 2 layers in this case. In this model, S and W media absorb light according to the Bird-Lambert model with optical absorption coefficients beta sub S and beta sub W. The set of differential heat diffusion equations must be complemented with the usual conditions of heat flux and temperature continuity across the interfaces and the limiting conditions of vanishing temperature as X goes to plus or minus infinity. The analytical solution is very complicated, but in the appropriate theoretical conditions, it reduces to this very simple exponential expression. In this, H is a complex constant independent of the sample thickness. The amplitude decays exponentially with the optical absorption coefficient, as is evident. Here is a cross-section of the experimental setup. The layer between sample and paleolithic sensor is a protection material for this last. This is a picture of the actual photoparalytic setup in my lab. Diode lasers at 904 nanometers, 980 nanometers, and 1064 nanometers were used as light sources. The Stuber method, with some modifications, was used for nanoparticle synthesis. Silicon nanoparticle size of 673 nanometers were obtained as a result. Experimental results for silica colloidal suspension at 0.0533 milligrams per milliliter and at a wavelength of 904 is shown in these 2 plots. The left side plot shows the photoparalytic phase, while the right side plot shows the paralytic amplitude in semi-log scale as a function of the sample thickness. The left plot shows the sample thickness range where the paralytic phase is constant and where a confident linear fit can be carried out. This is shown as a straight line in the plot on the right. The corresponding optical absorption coefficient is shown on the same plot. Similar results for the same sample at a wavelength of 1064 nanometers are shown on these 2 plots. This table summarizes the optical absorption coefficients for all samples at the 3 different wavelengths. The absorbance for all samples at 904 nanometers and at 980 nanometers were measured using a conventional spectrometer. The plot at the left side shows the behavior of this parameter as a function of the silica concentration. No linear correlation was obtained, an indication that this Lambert model does not apply for these colloidal suspensions at the range of concentrations. On the opposite, the right side plot shows the corresponding optical absorption coefficient measured by means of the photoparalytic technique. The linear correlation is evident in this case. Similar results are shown, but at 980 nanometers in this case. Optical absorption coefficient as function of silica concentration is shown in this plot at 1064 nanometers. The corresponding absorbances were not measured due to limitation of the spectrometer. It's important to point out the non-linear correlation of this optical parameter at this wavelength in this case.